Hello, and welcome back to sections 19.3 through 19.4. In this video, we'll be looking at an example that has eccentric impact. So that is going to be when we have a planar rigid body impacted by either another rigid body or a particle. So the fortunate thing is our coefficient of restitution equation stays the same. So it's that same equation that you wrote for particles. The only thing we have to be careful about is creating our lines of action. So what we have here is we have this plane between the two bodies. I know I didn't quite get it on there. This would be our plane that would define it. They're interacting here at this point. So they should be tangent to the bodies. And then you will have what we would call our X, or our line of action, line of impact, sorry, over here. So note that this does not have to go through the center of gravity of either of these bodies. So make sure you can get that. Alright, so let's look at our example. So our example is a lot like example 1 in the sense that we have a slender rod hanging down and we have some particle that's going to run into it, except this time that particle is not going to stick, it's going to bounce off of it. We're still asked to find omega 2. Alright. So I redrawn that here. Slender rod fixed at A. We have our particle. So I'll call this B. It's a ball. It's going to run into it. It's going to so our line of action is dictated by this thing's velocity. So it's going to act here 2 feet down from A, but our line of action is actually going to continue with this dashed line. So this is our, not line of action, line of impact. So our line of impact is dictated by this velocity in this case, and it will go through this particle just because particles have no size. So the only place it can touch the particle is through the center of it. But our center of gravity is like up here somewhere for this thing, and it's not going through that. So our goal is to find omega 2. I'm going to assume omega 2 goes this way based on kind of what we think is going to happen. We've been given all this stuff. So let's start off, just as we did with example 1, with conservation of angular momentum. Again, I'm going to go about the fixed point A here. I could go about this point G, but then I have to find these reaction forces, and I don't want to do that. I'm going to assume this direction because this is my omega 2. It'll make it easier when I put on my omega 2s. Equal to sum of the angular momentums about A at state 2, where again, this is time 1, this is time 2. So right before impact, right after impact. Let's break this apart. So we will have for the ball at 1, for the rod at 1, for the ball at 2, and for the rod at 2. Again, the rod is not initially moving, it's hanging down, so this will zero out. And unlike the last time, we'll be able to find this because we have all the information for it. But we're going to have 2 unknowns, which means we're going to need another equation. So let's go ahead and get what we do know. So we know the ball. We're going to use dmv again. So again, distance times the mass velocity of the ball. And then plus 0 for the ball at state 2. This is again going to be dmv. So this will be velocity 1, this will be velocity 2. And then for the rod, we can use the IA for the rod and omega 2, which is what we want to find. Okay, so let's put in what we know. The ball is going to be 2 feet away from A, so I'm doing all this about point A, remember. So it is 2 feet away from A. The mass of the ball is 1 pound divided by 32.2. Because these all have a mass term in them, you could get away with just using pounds because the 32.2 should cancel out, but let's just be safe. Velocity 1 was given as 50 feet per second to the right. We do want to check that this, we didn't do it last time in example 1, but check that if I push on it this way, it will cause rotation this way, which it does, so we don't need to add any negative signs to fix the sense on this. Alright. When it leaves after impact, it's still going to be 2 meters away. It's still going to be 1 over 32.2, but I will not know what velocity 2 is. For IA, we're going to use that same 1/3 ml squared. 1/3 mass of the rod, and then L squared, omega 2. Let's just get some numbers. Actually, we'll just go ahead and plug in what we know here. So this is going to be a 6 divided by 32.2, and this is going to be, it's a 3-foot rod, so 3 squared. And we'll have our omega 2 over here. So as you can see, we have 32.2 in all of these. If I can just drop that term, makes our numbers prettier. That's the only reason I'm doing it. So we'll get 100 over here, 2 times 50. We'll get a 2 V2 over here, and we will get a 1/3 times 6 times 3 squared, so we'll get 2 times 9, which is 18 omega 2. So this will be our equation 1. Just like with particles, we need to get an equation 2. Our equation 2 will come from the coefficient of restitution, which we were given as 0.7. So we know that E is 0.7, and that is going to be equal to the difference in V2, so the exit velocities over the initial velocities. And then one of these has to be negative. It doesn't matter which one. So I'll just make the top negative. So for V2, we can have, so we need to be careful here. I know I called this V2. This V2 is not the same as this V2. So if you want to, I could call this V2B, just so that we aren't confused about that. So if I have V2, actually, we'll have V2 of the rod minus V2 of the ball. So I chose to put the ball negative because I expect the ball is going to bounce back this way, which should be negative, so I'm assuming that this is our positive direction. And so I'll actually get to add these numbers up. And that means that I will have V1 of the ball here minus V1 of the rod here. The rod is initially at rest, so this zeroes out. V1 of the ball in this direction. So again, this is our x direction, which is our line of impact. So it has to be the velocity along this line of impact. So if B was at some angle, we'd use a cosine to get that component in the correct direction. All right. So 0.7 equal to, so that means it's all going to be in that direction, and it is 50. And minus V2 B for the ball. V2 rod, so for the rod, we're going to use some kinematics, knowing that this is 2 feet down. So V2 of the rod, if it's going to rotate this way, omega 2, or I'm sorry, I'll scoot that up, then V2 rod should be omega 2 times 2. So omega r, just like we've done before. And we are assuming this to the right, we're assuming this matches what we've assumed already before. So no sign fixing here needs to happen. So we will just put in an omega 2 times 2 here, so we don't create a new variable. Alright, so let's clean this up. Alright, so I will get a 35 on this side equal to 2 omega 2 minus V2 of the ball. I only need to find omega 2. I do not need to find V2b. So what I'm going to do is I'm going to solve one of these two equations for V2b and sub it in to the other. I'll just do this one because it's already here. So V2b down here will be 2 omega 2 minus 35. We'll add it there, we'll subtract it there. Basically, we'll just flip-flop these two pieces. And we're going to sub into equation 1. So that means equation 1 will become 100 equal to 2 times quantity, 2 omega 2 minus 35 plus 18 omega 2. Scoot that up, sorry about that. Omega 2 is my only variable. You solve that for omega 2, and you will get 170 divided by 22. So basically you're going to get a 70 here, move it over, and you'll get 22 times omega 2. And that is in fractional form is 7.727 radians per second, and it is positive, which means that we guessed correctly. All right. So hopefully that helps. If you have any questions, feel free to reach out.